Alright, so we are making our way from the unit circle, and then in the last section we talked about right triangle trig. So take a point anywhere on here, and again I'm always using quadrant 1. We don't have to, we can put this point anywhere. Alright, so I put this thing in quadrant 1, and I'm going to put a dashed line that connects the origin to that point. Alright, and then that's our radius. If I drop down from that, then I've created a right triangle. Okay, and that angle is what we rotated from the positive x-axis up to this point, and we drop down from wherever that point is to the x-axis, and that's x, that's y, that's cosine, that's sine. This is radius 1 as it stands right now, and we've created this right triangle. Now in the very first section we defined sine and cosine and tangent, and then eventually secant and cosecant off of that angle. So it just rotated by some angle on the unit circle, and we could find sine, cosine, tangent. Now in the second section, or right triangle trig, in the next section, we removed this triangle that we created in the original unit circle, and we said, hey look, the circle's gone, but this was still sine and this was still cosine because the hypotenuse of that right triangle is 1. But then we said, okay, well I could take this triangle and I could create a larger triangle just by making the triangle bigger, and this angle is still the same angle that it was to begin with. The angle's preserved, and this is a 90-degree angle, so it's preserved. So these are similar triangles. And then I could take this right triangle and say, well, the sine of this angle is opposite over hypotenuse, the cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. And we could do that just based off of the properties of similar triangles. Okay, the ratio of side lengths have to be preserved in similar triangles, and since I literally just pulled this off of there and then blew this up, those are similar triangles, and so tangent is opposite over adjacent, sine is opposite over hypotenuse. Now here's the last part. This is what we're going to do in this section. So first of all, notice I removed the side lengths from there. I'm going to regroup all these things, make them all one big triangle. And what I'm going to do is I'm going to take this thing and stick it back inside of that circle. Okay, but instead of this unit circle that had a radius of 1, now I'm going to make a circle centered where this thing was, and now the circle is going to extend out to the end, so it's got a longer radius. So this circle, I'm going to make it a blue circle. Oops, no field, sorry, I meant to make the outside blue. Alright, and then this inner circle, that was the one that corresponded to the red. Now the red one was our unit circle. This outer one, that's what we originally, when it was out here, we were calling it the hypotenuse. But just because it's bigger than that red one, we know that h is greater than 1. So it's not 1 anymore. So what are we going to call it? Well, since it's now the hypotenuse of that old right triangle is now the radius of this blue circle, we're just going to call it r. So it's just the radius. All right, now this point before, this point was just some xy coordinate, and x was the cosine and y was the sine. Now this point that's on this thing, the x coordinate goes out a little bit further than it did before, so it's not going to end up just being the cosine. Okay, we're out beyond, remember here's 1, 0, we're out beyond 1. That 1, 0 corresponded, let me make sure we understand that. That 1, 0 corresponded to the red circle, and this blue one, and now the x coordinate is out beyond that. Way over here, that would be r0 if we went out to the blue circle, so if we're out here where r units away, whatever r is, if that rotated down, that would be r still. So the point is now x can be bigger than 1, all right, and y can be bigger than 1. So it can't just be sine and cosine, because remember the biggest that sine and cosine could be was 1. So we're actually going to be multiplying sine and cosine by something to get these values, and we'll get into that in just a little bit. So this was x, this was y. All right, well, this blue piece right here, from here to here, let me kind of delete the red for just a second, just so we can see it. This blue piece from here to here is the x-coordinate. All right, and from here to here is the y-coordinate. So once again, I'm going to peel away that right triangle from the fact that it's inside a circle, and I've got a right triangle again. So I can talk about right triangle trig. And I can say, well, the cosine of this is adjacent over hypotenuse, and the sine of this angle is opposite over hypotenuse. The tangent is opposite over adjacent. And so what we get is we can now redefine the trig functions back inside a circle. So the last time we left the circle and came to right triangles. Well, now we're taking those right triangles and going back to circles, and these things could now be in a circle of any radius. So we don't have to be confined to a radius of 1 like we were when we first defined sine and cosine, and we don't have to be in a right triangle, even though we could create a right triangle anytime we wanted to just by doing what we did, pulling them out of the circle. But the key thing here is now we're going to be able to use any radius. The extension of what we were doing before when it was a unit circle with a radius of 1 to a any circle is the only thing that's different is we have a little bit bigger, and again I did the inside instead of the outside. This was our unit circle. This is the blue circle on the outside. Changing the circle's radius just creates similar triangles again, just like we saw before. These similar triangles that we saw back in the last section are equivalent to, I guess I should say, changing the radius of the circle, because every time you change the radius you get a different hypotenuse, but because they're all right angles, we get a whole family of possible right triangles that we can make. So let me do another just so you can see. So if I extend it out even beyond that one, I would have then other circles with different radii. And I could go inside the unit circle now, and I can make circles with a radius even that's a fraction, like a quarter or a half or something. And then I could have a whole different family of different radius that I could create. And every one, if I went on the intersection of this line and created a right triangle from that, then I can just keep doing this process over and over again. I can make a whole bunch of similar triangles like we did in the last section and show that the sines and cosines and tangents would be the same for all of those. So it's basically the combination of the last two sections coming together for this section to make any circle that we want. Okay, and we're basically using right triangle trig to create this property. So what we're going to see here is cosine is going to be, instead of just x like it was for the unit circle when the radius was 1, it's going to be x over r. Alright, so when r was 1, x over 1 was just x, and the cosine was just the x coordinate. Sine was just the y coordinate because it was y over 1. Well, now it's just going to be y over r, whatever r is. And so we end up with a slight alteration of what it was initially when it was the unit circle. So for any point in the plane, the sine of that angle that rotated to get to that point is y over r. The cosine is x over r. Tangent is opposite over adjacent, or y over x. And then the other three, just like always, are the reciprocal of these first three. Alright, so -3, -5 is a point on the terminal side of some angle theta. Find all the 6 trig functions. So just to kind of give you a visual here, we got our x-axis, our y-axis. Alright, let me make those solid. And black. Okay, and then -3, -5, so that would be -3, -5 down here. And so that means there's our terminal side, so we rotate it all the way down to here. Okay, so find the 6 trigonometric functions. Well, this is x, this is y. We're just going to use these definitions for these things. We're going to start with the first 3, the main 3, but to be able to find the trig functions, we only have x and y. What do we need? We need r, right? Because r shows up in these things. So this is what we're going to use to find those. Pythagorean theorem. The radius is the square root of x squared plus y squared. So we start off by doing that. R equals the square root of the -3 squared plus the -5 squared. That's 9 plus 25, which is 34. So we're going to start off with that, and then we just start setting up our trig functions. So sine equals y over r, that's -5 over the square root of 34. Alright, and then if you want to rationalize it, you can just multiply top and bottom by the square root of 34. That'll get rid of the square root on the bottom and give you an extra square root of 34 on the top. But it's fine with me if you just leave it with the square on the bottom. Alright, cosine is x over r, alright, and then tangent is y over x. So -5 over -3, they're both negative, so drop the negatives and give you 5 over 3. Alright, and then remember the other 3 are the reciprocal of those first 3. So cosecant, secant, and cotangent, you just flip these original 3 over, and you've got the other 3. Alright, evaluate, if possible, the sine and the tangent of the following 4 angles. So our quadrantal angles. The quadrantals are 0, 90, 180, 270, pi over 2, pi, 3 pi over 2. It's just moving around that positive x and y axis, the negative x and y axis. So the sine and tangent of each one of these. So the sine of 0, the tangent of 0. Remember, sine is the y coordinate, tangent is the slope. So in this case, they're both going to be 0 because, if you think about it, if I've got the positive x-axis over here, if I haven't rotated any at all, then I'm out here somewhere. So the sine coordinate is whatever x is, and 0 because we haven't gone up, so the sine is the y. Now it's not just the y, it's going to be y times something. We'll get into that later. But I haven't moved up, so it's just 0 here. Okay, and the tangent is the slope, so that's a horizontal line, so the slope is 0. Alright, part B, what if it's 90 degrees? Alright, well, the sine of 90 degrees, again, go back to right triangle trig, the sine of 90 or the sine of pi over 2. If I am rotated 90 degrees, I'm up here on the y-axis. Right, I've rotated 90 degrees, so I'm up here at the y-axis. And remember, in the unit circle, sine is the y-coordinate, so that's 0, 1. So the y value is 1 at 90 degrees. Alright, the tangent, now that's a vertical line. It's not a very good picture. That's a vertical line segment, and the slope of a vertical line is undefined. Okay, so it's not possible to define the tangent function. It's undefined. Alright, and then at 180 degrees, so if we take this thing, and now we're all the way back to here, that's the angle we've rotated. We've rotated, instead of just there, we've gone all the way 180, or pi radians. Instead of this being 0, 1, it's -1, 0. So that's not a very good picture, but the sine is the y-coordinate, so we're back to 0, right? Tangent is the slope, that's a horizontal line again, so we're back to 0. And then finally, 3 pi over 2, that's the negative y-axis. So down here, the y-coordinate is going to be -1, Alright, and then it's going to be vertical again, so it's undefined. Alright, reference angle. This is a huge idea for moving forward. Okay, so once again, if you can memorize what happens in quadrant 1 and how we progress through quadrant 1, then we can make our way through all the other quadrants based on the acute angles that we got in quadrant 1. So in quadrant 2, all the angles that we're dealing with are, remember the symmetry's coming from the y-axis here. So when we rotate clockwise to get there, whatever angle that we're doing to get there, the y-coordinates, the x-coordinate, the tangent, all those things are going to be the same absolute value, meaning the same number, maybe not necessarily the same sign, but the same absolute value as if we had rotated this same angle, which is called our reference angle, up here. It's just the y-coordinates are going to be the same, the x-coordinates are going to be opposite, the tangent's going to be opposite, if you see right there. But the reference angle will give us all the same absolute values, and then we just have to think about, alright, which quadrant are we in? So the reference angle gets everything back into quadrant 1, and we can think about how things would have happened in quadrant 1, and then just apply the signs, the correct signs, based on which quadrant that we're in. So whatever, to get a reference angle if you're in quadrant 2, to find that same angle that would have occurred in quadrant 1, what you're basically doing is you're starting from 180 or pi if it's radians, and you're going back whatever this theta prime, which is the notation we use for a reference angle. So 180 minus whatever the angle theta was will give you a reference angle, will give you basically this same angle in quadrant 1, and then you can just use whatever sine and cosine and tangent are for that reference angle. Okay, that's the idea here. Alright, so this is 180 minus pi, it's also pi minus theta if you have it in radian measure. Okay, now if we're going beyond that, if we're in quadrant 3, then our reference angle is going to be if we extended this line straight through back into quadrant 1. So we just keep on going right back into quadrant 1, and there would be our reference angle. Let me move this down and make it kind of a little more accurate. So our reference angle would be this little guy right here. Right, that theta prime, if I applied that just from the positive x, that theta prime right there, that extra little bit, that's the acute angle that gets me back into quadrant 1. And again, the sine value, you know, where, depending on where I stop on this thing, it's now the opposite. You know, the y's are the opposite. The x's are also the opposite. So because instead of going right and up like I would in quadrant 1, I'm going left and down. So the x is the opposite of what it would have been. The y is the opposite, but the absolute values are the same because of the way the angle works. Okay, so we've created an acute angle. What angle would that be? Well, we're going to take the angle measure going all the way around, that's what theta is given to us, and we're going to subtract off from there, we're going to subtract off 180 or subtract off pi, and that'll leave me with this little tiny angle right here. Okay, so that's how we come up with a reference angle if we're in quadrant 3. And again, if this were radians, it would be theta minus pi. Alright, and finally in quadrant 4, we're now using the symmetry at the x-axis. So instead of going all the way around to here, what we're saying is if we just take 360 and subtract that angle, we would get an acute angle. Okay, we're in this last quadrant, so 360 minus whatever this angle is would leave us with an acute angle, and that would be similar to if that acute angle were in quadrant 1. Again, now our x-coordinate is exactly the same. Our y-coordinate is opposites, and our tangent is opposites. Here, the x-coordinate's opposite, the y-coordinate's opposite, but the tangent is the same. Okay, because it's the exact same line, it'll have the exact same slope. So 2 of the 3 are opposites, and then 1 is the same every time that we make these adjustments. All right, and remember 360 is the same as with radians, is the same as 2 pi minus the angle if the angle is given in radians. All right, so find the reference angle. 345, where are we? For 345, we are in quadrant 4. So we're going to take that thing and subtract from 360. Okay, now 5 pi over 6. Well, where would we be if this were radians? So if you don't know your radians, what you can do is know this is 0, this is pi over 2, pi, and 3 pi over 2. So there's the decimal equivalents for pi over 2, pi, 3 pi over 2. So 5 pi over 6, if I look at 5 pi over 6, I get this number, 2.61. That's between 1.57 and 3.14, so that's between pi over 2 and pi. So that means 5 pi over 6 is in quadrant 2. Okay, so in quadrant 2, what do I do to get my reference angle? I take the angle, right, and I subtract that from, and in this case because it's radians, I subtract it from pi. So pi minus 5 pi over 6, that's 6 pi over 6 is the same thing as pi. So 6 pi over 6 minus 5 pi over 6 is pi over 6. Alright, now negative 135 degrees. What would my reference angle be? Negative 135. So instead of going this way, I'm going this way. So negative 135 degrees, there's negative 90. Alright, there's negative 180. So I didn't quite go negative 180. I stopped past 90, but beyond, beyond 90, but not quite negative 135. So it's in quadrant 3. Alright, but because it's a negative angle, what I'm going to do is I'm going to treat it as if it were a positive angle. So I'm going to flip this up and down. And so I am in quadrant 2. So I'm actually going to do the property as if I was quadrant 2. I'm going to ignore the sign. So pi minus 135. Alright, and then I'm going to treat it as if it were a quadrant 2 angle, since that would be the definition of this, right? The reference angle is the positive acute angle formed by the terminal side. So yes, I would be technically down here in quadrant 3, but to get the reference angle, it's off of either the positive x-axis or the negative x-axis for all of these, you notice. So to get that reference angle, I'm going to ignore that sign and then put myself in the quadrant based on if it were a positive angle. Alright, that'll give me the reference angle. Again, all we're trying to do is create an acute angle, a positive acute angle that gives us in quadrant 1, so we can figure out what's the sine, the cosine, the tangent, those special angles, and then we are going to apply the sines of the different quadrants to get the sine of the special angles, like the sine, cosine, the tangent. Alright, now theta equals 2.5, that's radians. Okay, so this is degrees, this was degrees. They're not a degree symbol there, so we're assuming that's radians. So once again, what we saw before, this is pi over 2, this is pi, so 2.5 is between these two numbers again. So once again, we're in quadrant 2. So we're going to take pi, right, pi for quadrant 2, and subtract the angle in radians, and we're getting about 0.64. Okay, on your calculator, pi minus 2.5, it gives me this, and so that's where that's coming from. Alright, so just depending on what your original angle is, get a positive version of that angle, and then find the acute angle by either subtracting from pi, subtracting pi from the angle if it's quadrant 3, or subtracting from 2 pi if you're in quadrant 4. Alright, now this is completely up to you if you want to do it this way, but this is the way I do it. I always associate the angle that they give me with a reference angle, and then find the function value for that reference angle, and then apply sines for that. Right. So if you remember your quadrants, right? If we're up here in quadrant 1, then both x and y are positive. So that means because x is positive and y is positive, remember this is cosine, this is sine. So cosine will be positive, sine will be positive, right? And since sine and cosine are both positive, and tangent is sine divided by cosine, tangent's also positive. Alright, so everybody's positive. Now, in quadrant 2, we're to the left of the y-axis. So cosine is now negative. But we're above the x-axis, so the y value is positive. So that means that cosine is negative because we're to the left, so the x values are negative. Sine is still positive, but tangent is sine divided by cosine, or positive divided by negative. So tangent is now negative. Alright, so sine is the only one positive in quadrant 2. Alright, now remember, if cosine is negative, then secant is negative. If sine is positive, then cosecant is positive. And if tangent's negative, then cotangent's negative. Remember, the other three are just the reciprocals of these, so signs aren't going to change. Now, quadrant 3. Now, in quadrant 3, we're to the left of the origin and down. So the x-coordinate's negative and the y-coordinate's negative because we go left and down. So that means cosine is negative, sine is negative, but since tangent is sine divided by cosine, a negative divided by negative is a positive. So now the tangent's positive. And then finally in quadrant 4, we're to the right and down if we're in quadrant 4. So the x-coordinate's positive because we went right, but the y-coordinate's negative because we went down. So cosine, remember that's associated with x, that's positive. Sine is associated with y, that's negative. Tangent is sine divided by cosine, so a negative divided by positive is negative. Okay, and remember reciprocals are going to be the same. Secant's positive, cosecant's negative, cotangent's negative. Alright, but what I want you to see is here everybody's positive in quadrant 1. Alright, so all. Alright, here only sine is positive. So in quadrant 2 is just the sine function. Alright, quadrant 3, it's only tangent is positive. Alright, and then finally in quadrant 4, it's only cosine. Alright, and there's this little mnemonic to help you remember this. So it's A for all, S, T, C. So A, S, T, C. The way that I was taught this, the way I went to Appalachian State, so the ways I was taught it was Appalachian State Teachers College, right, which is what it used to be called before it became a public university with other things that you can major in. It used to be a university where they trained just educators. So it used to be called Appalachian State Teachers College. So that's the way I always remembered it. But if you remember the sine is associated with y and cosine is associated with x, then you can remember if you're to the right, then cosine's positive. If you're to the left, cosine's negative. If you're above the x-axis, sine is positive. If you're below the x-axis, sine is negative. And then you just have to remember tangent is one divided by the other. You can kind of derive these sine patterns based on that. Alright, so let's use reference angles to come up with these things. So remember 14 pi over 3. So first of all, 14 pi over 3, 6 pi over 3 is 2 pi. So 14 pi over 3 is much bigger than 2 pi. So we've gone beyond one rotation. So before I even get into reference angles, I've got to get inside one rotation around. So I'm going to subtract 2 pi because that's, remember, subtracting 2 pi gets us from where we were back to the same place, but with a smaller angle. So I've got 8 pi over 3. That's still bigger than 6 pi over 3. So I'm still not within one rotation in a regular circle. So because I'm still larger than 2 pi, I'm going to subtract 2 pi again, and that's going to get me down to 2 pi over 3. All right, now 2 pi over 3 is in quadrant 2. So what did we do in quadrant 2? We subtracted from pi. All right, so pi minus 2 pi over 3 is pi over 3. So what I'm going to do is I'm going to find the tangent of pi over 3. All right, the tangent of pi over 3, if you go back to your unit circle, that's the steep one. So for tangent in quadrant 1, remember we get either 1 over the square root of 3, 1, or just the square root of 3. And pi over 3 of those 3 special angles in quadrant 1, pi over 3 was the steepest, so the slope is going to be the biggest, or the biggest of the 3. So the tangent of pi over 3 is the square root of 3. Now, we're in quadrant 2. Okay? Remember, in quadrant 2, the tangent is negative, because in quadrant 2, remember, just to visualize it, if we're in quadrant 2, that means our special point's here somewhere. We're coming downhill. All right, and tangent is slope. Slope is negative if you're coming downhill. So our actual value for the tangent is going to be negative square root of 3. Okay, and you can verify that with your calculator. Tangent of 14 pi over 3 is that. The negative square root of 3 is that. Okay, so that's how the reference angles work. We get an angle in quadrant 1, right, or via a reference angle. We get into quadrant 1, we find our value of that reference angle, but then we go back to the fact of which quadrant are we in, right? 2 pi over 3 puts us in quadrant 2, so the tangent of that thing is the opposite. It's the negative square root of 3, because we're coming downhill rather than, this is our reference angle in quadrant 1, we're going uphill, so it's positive. But since we're in quadrant 2 and our reference angle is this right here, right, the tangent's negative. All right, for part B, secant, the secant of negative 17 pi over 4. Same thing as before. I'm going to add, because 17 is negative 2 pi, would be negative 8 pi over 4. So I'm more than one rotation. So I'm going to add 2 pi this time and get negative pi over 4. That's still bigger than negative 8 pi over 4. So that's still bigger than 2 pi. So I'm going to add another 2 pi, or 8 pi over 4, and that gets me to a negative pi over 4. Okay, that's quadrant 4. All right, and remember, for negative acute angles, its reference angle is going to be the positive acute angle. All right, so if we're down below in quadrant 4, it's the same thing as if we're above in quadrant 1, because it's a negative, it's acute angle, so that's what we want, a positive acute angle. So we just drop the sign, and that'll be our reference angle. So our reference angle for this secant is going to be pi over 4. And remember, secant is the reciprocal of cosine of pi over 4. So the cosine of pi over 4, probably you may have it on your sheet, your unit circle, as the square root of 2 over 2. And that is true. But this time, instead of rationalizing the numerator, we're going to rationalize the denominator. Rationalize the denominator, we'll rationalize the numerator. And what we end up with is square root of 2 times the square root of 2 is just 2. And on the bottom we have a 2 times the square root of 2, and the 2's cancel, and leaves us with a 1 over the square root of 2. So square root of 2 over 2, 1 over the square root of 2, the same thing. I'm using the version that's 1 over the square root of 2 because I'm needing its reciprocal, and it's easier to see the reciprocal here is just going to be the square root of 2. Alright, now this is quadrant 4. Alright, in quadrant 4, cosine and secant are both positive. So I'm getting a positive here because I'm in quadrant 1. Everything's positive in quadrant 1. In quadrant 4, we have to think that we're down now below the x-axis. We're down here. And secant is the reciprocal of cosine. Cosine's x. If we go quadrant 1, x is positive. If we go quadrant 4, x is also positive. So we'll keep the positive version. Alright, and then we get, just to check, the cosine of pi over 4, that little negative thing that you see on your calculator, this little button right here, will let you go from cosine to secant. Okay, you start with cosine, but you have to use that -1 to get to secant. So the cosine of pi over 4 to the -1 power is the secant. Alright, and then the square root of 2, we see that it is correct, though we do have the same value. So that's how we use these reference angles to come up with the sine, cosine, tangent, secant, cosecant, cotangent of these numbers that are not acute angles. Right? So we need acute angles for right triangle trig. We have to have acute angles. Everything has to be acute because we can't have obtuse or these huge angles in a right triangle because we can only have acute. But in this section now we can take angles of, you can have any angle. It doesn't matter what the angle is. We just have to get these reference angles to get us back to acute angles so we can do the trigonometry on the acute angles that, since we know them, back in quadrant 1. And then we have to apply the sines. Right? Which quadrant are we actually in? And then think about what this particular trig function would be in that quadrant to be able to get these values down. So it's very important that we understand the sines and the different angles. All right, so this little slide right here, if you want to pause this thing and print this out, or I can just print it out for you and post it. This is everything, just about everything that we've talked about up till now. The unit circle, how the angles are formed on the unit circle, negative angles on the unit circle, the sine, cosine, tangent for the special angles inside that first rotation around in quadrant 1, and then there's the positive x, the positive y, the negative x, the negative y axes. All right, and coming up with these reference angles. All right, so it's very important that we'll get a plus or minus based on which quadrant we're in, and that's where this comes into play.